If you're training to be a pilot, you probably noticed that pilots have to know a lot about the weather. One of the biggest reasons for this is so we can avoid hazardous weather. In this video, I want to specifically talk about 6 different hazardous weather conditions. I also want to explain when you should be looking for them and tips to avoid them. In order to completely understand this video, you need to have a decent understanding of the weather and what causes it to change. You might find this video much more useful if you watch my video on weather basics first. If you haven't already watched that, I'll put a card right here and a link in the description. Then you can watch this one afterwards. The first hazard you really need to know about is a temperature inversion. Now this might seem confusing because a temperature inversion means that the air is really stable. Why would that be so hazardous to a pilot? That seems kind of nice to me. Before we talk about why that is, let's briefly explain what a temperature inversion is. A temperature inversion is when the temperature actually goes up as you increase your altitude. As you may remember, this is not normal. One way this can happen is on a cool, clear night when there are no clouds to trap the heat near the earth. Because of that, the ground cools very rapidly, and in turn, that cools the air next to it and leaves the air at higher altitudes relatively unchanged. Now we have warmer air above and cooler air below. Another time this can happen is in front of a warm front. As the warm air from a warm front pushes into cooler areas, some of the warm air is lifted above the cooler air. And once again, this causes an inversion. The difference between these two examples is that on a cool, clear night, the inversion happens near the surface. On a warm front, the inversion can be at a high altitude if it occurs a long way in front of the warm front. But as you can see, the closer you are to the front, the lower the inversion is. Now here's the problem. As we mentioned earlier, in a temperature inversion, the air is extremely stable. This means that it's resistant to vertical movement. Now while this does mean that the air will be nice and smooth, there is another problem that we run into. When there's a lot of humidity in the air, that moisture tries to rise, but it can't because that warm air is lighter and it traps that moisture at low altitudes. This can mean low clouds, fog, haze, or mist. Basically, this causes bad visibility and clouds at low altitudes. If you're a VFR pilot, you can see why this could be a problem. But for my IFR students, this can also cause your ceilings and visibility to be below minimums, and those need to be above minimums in order to legally fly an instrument approach. Okay, so let's talk about fog for a minute since we're on the subject. There are 5 types of fog, but 4 different types you should be familiar with as a pilot. Radiation fog is what you might get on one of those cool, clear nights where the moist air near the ground cools rapidly. As the air cools, if it's cool enough to reach its dew point and it's not too windy, radiation fog will form. And any wind can cause radiation fog to dissipate. Because of this, you will often find it in low areas like valleys between mountains and hills where it can be shielded from the wind. Advection fog is a little different. This occurs when warm moist air is pushed over a colder surface. The cold surface cools the moist air to its dew point, which causes fog to appear. This sometimes happens in areas near the coast during the winter time. As you may remember, water cools and is heated more slowly than the ground. Because of this, the air above the water is typically warmer during the winter. If any wind up to 15 knots pushes that warm moist air over the cool ground, the air will condense and cause advection fog. Winds above 15 knots will often lift the fog and turn it into low-level stratus clouds. Next, we have upslope fog. This occurs when warm moist air is pushed up a sloped area of the ground like a large hill or mountain. As the air is pushed up, it cools down, and if it hits its dew point, once again, fog occurs. This is a type of fog that can last for days and can also appear at much higher levels than most other fog. One thing to remember about upslope fog and advection fog is that they both need wind to occur. Next we have steam fog. This occurs when cold, dry air is pushed over the water that is relatively warmer. As the water evaporates, it's cooled by the cool, dry air which causes it to condense and form a smoky-looking fog. This typically only occurs during the coldest parts of the year. One thing you want to remember about steam fog is that it's not uncommon to see icing conditions and low-level turbulence in these areas. Okay, so how can we avoid bad visibility and low clouds caused by these temperature inversions and frontal systems? First, be aware of warm fronts and avoid the leading edge as much as possible. You can know where these are by taking a look at the surface analysis charts, and I explain these in a lot more detail in some of my other videos. Second, if it's a cool, clear night, remember this can cause low clouds and other types of bad visibility. Consider planning for a later takeoff. Third, recognize coastal areas and mountain areas when the different types of fog can occur and pay attention to the direction of the forecasted wind. The second hazard I want to discuss today is wind shear. Wind shear is one of the scariest weather hazards there is, primarily because it gets people when they least expect it. Wind shear is a sudden change in wind speed and/or wind direction that occurs in a small area. These changes in wind speed and direction can occur at any altitude, and the changes in wind direction can be vertical as well as horizontal. With that in mind, these changes can have a huge impact on your aircraft's performance. For example, if you remember from our lesson on how an airplane creates lift, a wing needs relative wind in order to produce lift. The more relative wind that flows over the front of the wing, the more lift the wing produces. Now let's say, for example, you're landing in a 30-knot headwind at 500 feet, and at 499 feet, you only have a 5-knot headwind. This would be considered a type of low-level wind shear because the difference is more than 15 knots. Now, as you may know, your aircraft's approach speed is typically 1.3 times VS0, which is your stall speed in the landing configuration. Another way to remember this is SO stands for stuff out. Anyway, my approach speed is 60 knots. That means my stall speed is just above 46 knots if all my flaps are in. Now remember, our airplane doesn't care about how fast we're traveling over the ground. It only cares about how much relative wind is going over the wings. So if I have a 30-knot headwind here, and that all of a sudden drops to 5 knots, and I don't do anything, my new airspeed is 35 knots. That's more than 10 knots below stall speed. If this happens, you just exceeded your critical angle of attack, and your airplane is now in a full-blown stall. Now you're starting to see the danger of wind shear, and one of the reasons we practice stall recoveries. This type of wind shear, where the performance of our aircraft gets worse, is called performance decreasing wind shear. This can come in a few different shapes and sizes. You may see this example that we just talked about, or you may see the wind shift from a headwind to a tailwind, and this can be really bad. You may also see wind shear in the form of vertical air, which can not only push the aircraft up or down, but can also disrupt the airflow over the wings, which can destroy your lift and ultimately cause the aircraft to stall as well. Vertical movement of air like this is typical in thunderstorms, and we'll discuss that more here in just a minute. But it's important to know that the downdrafts a thunderstorm produces can be in excess of 6,000 feet per minute, and these are called microbursts. And thunderstorms can also create headwind losses between 30 and 90 knots. Now, some types of wind shear can actually increase the performance of your airplane, and we call this performance increasing wind shear. And this is what would happen if you got a sudden increase in headwind. Now, this one's not quite as dangerous as performance decreasing wind shear, but you still need to look out for it. Sudden airspeed increases can lead to you exceeding your aircraft's airspeed limitations, or even exceeding the G limitations if you also get into turbulence at the same time. Okay, so let's talk about some of the things that cause wind shear and how you can protect yourself. The first thing that can cause it is a temperature inversion, like we discussed earlier. When there's a temperature inversion, if the upper level winds are 25 knots or greater, it's not uncommon to see calm winds close to the surface, so this is something to be aware of. Another place you might find wind shear is near a passing frontal system, and this is for two reasons. First, warm fronts can also cause temperature inversion, but also there's typically a wind shift right on the boundary of a passing front, and this can sometimes be significant. So how do we avoid wind shear? Obviously, it's best to avoid flying near thunderstorms and frontal zones, but the more you fly, you're probably going to find yourself dealing with wind shear of some kind. The key to flying safely in wind shear is to 1. Avoid bad wind shear at all costs. 2. Know where it exists. If there's no way to avoid it, fly faster airspeeds if you know you're going to be dealing with performance decreasing wind shear. If I know there's 30 knots of wind shear right here, fly 30 knots faster. Once you hit that wind change, you'll be right on your airspeed. If it's a performance increasing wind shear, that's not quite as big a deal. Just make sure you pull the power back so you don't exceed any limitations. But now you're probably wondering how to know where there might be wind shear. One of the first places you'll see an indication is when you see a remark like this on the TAF or METAR. In this example, we can see that the wind shear is at 1,000 feet AGL, and the wind is at 180 at 40 knots. So if the ATIS is calling winds at 180 at 10 knots, this is when I might consider carrying 30 extra knots of speed until I get about 500 feet to be safe. Now you may also see notes about wind shear in the PIREPs, but one of my favorite places to look is the winds aloft tables. If you're a regular viewer, you know how easy it is to find these. Take a look at this line for the winds aloft near Tulsa. As you can see, at 3,000 feet MSL, the winds are 180 at 28 knots. If we looked at the METAR and the winds at the surface we're calling calm, then we know there might be a little bit of a wind shear here. I highly doubt that to be the case though, since you can see that the temperature decreases with altitude. So we know we don't have a temperature inversion, but notice here at TYS, we do have a slight temperature inversion. And I'm not super concerned about wind shear here either because the winds are only 5 knots at 3,000 feet. It's pretty rare to see winds increase as you get closer to the surface. I'm not saying it doesn't happen, but it's pretty rare. Then don't forget about those thunderstorms. Near these is where you'll find some of the most hazardous turbulence and wind shear there is. So thunderstorms are number 3 of the big 6 weather hazards I want to talk about today. As we discussed in my Weather Basics video, thunderstorms develop as a result of warm, moist, unstable air. Warm, moist air creates a lifting force, and the more unstable that air is, the stronger the lifting force and the more powerful these storms can be. Now typically, it's very common for thunderstorms to develop in front of cold fronts, especially during the summertime, and that's because the air near the surface is warmer, and this causes 2 problems. First, more evaporation, which adds more moisture to the air. Water vapor is lighter than air, so this makes the air rise more quickly. The warm air near the ground also wants to rise because it's lighter than the air above it. So now this lifting motion begins the process of a thunderstorm's development. In the first stage, these continuous updrafts cause cumulus clouds. So if you see these, you know you can expect winds that are going to be pushing up on your aircraft. In the next stage, we see that the storm has developed into a full-blown cumulonimbus cloud. This is what we call the mature stage. These are super dangerous for multiple reasons. First, you can get some crazy precipitation that can make it really difficult to see. Also, this is a stage where you'll most often see the biggest updrafts and downdrafts. And as I said earlier, these downdrafts can be in excess of 6,000 feet per minute, and this is what we call a microburst. And this is that vertical wind shear we were talking about earlier. Anyway, during this mature stage of a thunderstorm, there are a ton of scary stuff to be aware of. First is lightning. Now technically, it's only a cumulonimbus cloud until there's a lightning strike. Then it becomes an actual thunderstorm. But either way, I'm staying as far away from these as possible because they can also cause hail, tornadoes, gusty winds, and wind shear like we mentioned earlier. Last but not least, we have the dissipating stage. As a general rule, dissipating thunderstorms primarily produce downdrafts, but it's still something to avoid as much as possible. These can also be very powerful and super dangerous. Okay, so now that we've talked about how dangerous they are, let's talk about avoiding them. First, we know that we can find these in front of frontal systems, especially cold fronts during the summertime. In fact, it's not uncommon for huge lines of thunderstorms to develop at the leading edge of cold fronts. These are called squall lines, and they can be hundreds of miles long. Thunderstorms at the leading edge of a cold front can also be particularly dangerous because they overtake warm, moist areas. This feeds them with fresh lifting energy. One other way you can find out about thunderstorms is called a convective signet. This is a type of in-flight weather advisory that is specifically designed to inform pilots of thunderstorms in the area. It can also give you details on some of the specific weather hazards associated with thunderstorms. These include storms with surface winds greater than 50 knots, storms with hail 3/4 of an inch and greater in diameter, tornadoes, and they can even let you know when your flight instructor is going to be in a bad mood. Okay, well maybe not, but they should be able to do that. But one more thing they can do is they can also let you know about embedded thunderstorms. These are basically thunderstorms that are buried in other clouds, and you won't even know they're there because you won't be able to see them. So where can I find these convective signets? Well, one way is to call and get a weather briefing before you go fly. They'll tell you if one of these exists in the area you're flying. Another way is to call the FSS on the radio and get an in-flight weather briefing. You can even know that they exist before you call because ATC will often announce over the radio that they're available on all FSS frequencies in the area. Attention all aircraft, convective signet for the Tulsa, Oklahoma area. Numerous embedded thunderstorms reported north, moving east at 12 knots. Tops reported at 410. Further information available on all flight service frequencies. Now we know there's a convective signet out near Tulsa, and we can call the flight service station closest to us and get the details just like I explained in the last video. Okay, so now we know how to find out where they are. Now we can avoid them, but let's talk about some ways you can be safe if something crazy happens and you accidentally get too close or you mess up really bad and you actually find yourself inside of a thunderstorm, because these things can literally pop out of nowhere. Let's start by talking about gusty winds. What should you change about your landings if you have gusty winds? Well, if they're gusty crosswinds, one of the things you can do is land with less flaps if you have enough runway. This is going to keep you from getting pushed around quite as much. Your flaps catch a lot of wind during crosswind operations, so this can make things a lot easier. If the winds are straight down the pipe, consider adding half the gust factor, up to 10 knots, to your landing speed. If you're wondering what I mean by that, listen to these winds from tower. Alright, so here's something handy that you can use in the future. You can ask for winds without saying anything else. Say winds.
Wind 200 at 17, gust 26.
In this example, the gust is 26 knots, so I'll subtract my base wind speed from that. So our gust factor is 9 knots. Half of 9 is 4.5, so I'll just round up and add 5 knots to my approach speed. And that just gives us a little safety buffer when we make our landings. You'll find that if you don't do this on gusty days, roughly half your landings will be plopped in. And I personally like smooth landings even when it's gusty outside. Now let's say you're coming into land and the winds are calm, but there's a thunderstorm near the airport. Depending how close the cell is, the smartest thing may be to divert somewhere else. But if the winds are calm and it's far enough away, you may still be able to land. But what runway should you choose? Yeah, the winds are calm now, but with a thunderstorm close by, it's something important to think about. When we look at how the downdrafts flow out of a thunderstorm, they typically flow down and out. So if you're going to attempt a landing, make sure you take those potential wind gusts head on. If a thunderstorm is northwest of runway 31, I'd want to land on runway 31, not 13, because there's a potential that you might see some wind gusts coming from that thunderstorm. Any gust you take from the front will increase your performance. Gusts you take from behind will decrease your performance. Now let's say you messed up and got yourself right in the middle of a thunderstorm. What should you do? Your gut reaction may actually tell you to do the wrong thing. If you ever get into this situation, typically the first thing you'll experience is a performance increasing headwind that is followed by strong downdrafts, then a performance decreasing tailwind. With this initial increase in performance, pilots have been killed by pitching back down to chase their altitude because immediately after, they are pushed straight down into the ground by these downdrafts. The big takeaway here is that you should not chase your altitude if this ever happens to you. And this is true if you run into really bad turbulence as well. Focus on your airspeed and fly as fast as you can, but still stay under your maneuvering airspeed. This will help keep you from damaging the aircraft. Then, get out of there as soon as possible. If you hit a downdraft like this, your instinct may be to pitch up to maintain your altitude. In reality, this is the opposite of what you need to do. Pitch down and trade any altitude you have for airspeed. This is going to allow your wings to create more lift and hopefully you won't stall. Once you have enough airspeed, you can climb away from the ground. You're going to need every bit of airspeed you can get if you leave the cell with these tailwinds. Anyway, I hope you never need this, but it's something I wish instructors would discuss more with their students. The fourth hazard you need to be familiar with is mountain wave turbulence. This is something that can occur in mountainous regions in windy conditions. Anytime the wind blows through the mountains, the ridges can disrupt the airflow and cause really bad turbulence on the other side. The side where the wind is coming from is called the windward side. Any wind that hits the ridge will cause turbulence on the leeward side, but the real problems happen when the wind is 25 knots or greater and the flow is nearly perpendicular to the ridge. Now, this alone can cause some real problems, but when the air on the leeward side is very stable, or worst case you have a temperature inversion, this is when you get true mountain wave turbulence because any air that wants to rise after being deflected by the ridge is pushed down by that stable air, and this causes the air to rotate on the other side. This becomes even worse when there's a layer of unstable air below the stable air, because that can cause extremely violent rotational winds on the leeward side. Often in these conditions, you'll see these rotor clouds which can indicate really bad mountain wave turbulence. To me, these look like giant cigars. Anyway, you don't want to be anywhere near these things. Okay, so there are two other ways you can recognize mountain wave turbulence before you even get close. First, if clouds are beginning to form on top of a ridge, it's very possible that warm moist air is being pushed by wind up the side of the mountain, and that air is condensing and causing clouds, very much like upslope fog. In these conditions, this is where you start worrying about mountain wave turbulence if the air is stable. If the air is not stable, this can be a problem too because this is where you might see a thunderstorm. One other way you can identify high wind situations is when you see these standing lenticular clouds. These are kind of smashed looking clouds that would indicate winds that are 40 knots or more. So when it comes to mountain flying, fly on the windward side as much as possible. When the winds at altitude are 25 knots or more, or you see these rotor clouds or standing lenticular clouds, or even if you just see normal clouds at the top of a ridge, this can indicate that mountain wave turbulence on that leeward side. So that's really when I'd be concerned about avoiding that side. Our fifth weather hazard is icing. This is basically ice buildup on your aircraft in flight. This is scary for a few reasons. First, it changes the shape of the wings, which can reduce lift or change the angle of attack. Second, it adds weight to your aircraft, way more than you might think. It also increases drag on the aircraft and can even cause engine problems. Okay, so now that you know that, icing can occur anytime you're in visible moisture and the temperature is 0 degrees Celsius or colder. Invisible moisture can be clouds, rain, snow, sleet, freezing rain, basically any form of water. The worst icing you will get though is if you fly through freezing rain. Don't do it. It's a scary situation. Freezing rain typically occurs ahead of a warm front when the air that is being overtaken is below freezing. If you fly through this, you're going to see some of the most rapid ice accumulation there is. One indication of freezing rain is ice pellets. I don't know if this is the correct term, but I call that sleet. This would indicate freezing rain at high altitudes. Okay, so how do I avoid this? First, know the freezing level. As I explained in my video on prog charts, you can find the freezing level and fly below it. Guess what? You won't get icing below that line. You still need to be careful about carburetor icing though. If you are going to be flying through freezing temps, just avoid visible moisture. All you have to do is eliminate one of the ingredients for icing, and you'll significantly reduce your chance of getting it. One other way you can know about icing is through in-flight weather advisories. The two types that will warn you about icing are AirMets and SIGMETs. AirMets primarily are for light single-engine aircraft. They only tell you about lower intensity icing. An AirMet Zulu would be an indication that you can expect moderate icing in those areas. SIGMETs are warnings of bad weather for all kinds of aircraft. One type of SIGMET you would see is a warning for severe icing. And just like the convective SIGMETs, you can get these AirMets and SIGMETs from any flight service station. You can also find them on the aviation cloud forecast, as I've mentioned in my past videos. One more thing I want to mention about icing is that training aircraft have very minimal anti-icing or de-icing equipment. In these aircraft, you should avoid icing to the max extent possible. As you begin to fly commercial aircraft, these may have anti-ice capabilities. Just remember, every aircraft can only handle certain levels of icing. Never fly into areas that are worse than the airplane's capabilities. But I would go one step farther and say avoid icing and get out of it whenever you can. Light icing can turn into severe icing in a matter of seconds. Our sixth and final weather hazard today is frost. This is something that happens on the ground before you take off. If you leave your airplane outside overnight and there's any moisture in the air, when the surface of the aircraft cools to the dew point, the air against it will condense and form dew. If the surface of the aircraft is below freezing, the dew will turn into frost. Frost is dangerous for two reasons. First, just like ice, it makes the aircraft heavier. But more importantly, it disrupts the laminar flow of the relative wind over the wing, which can destroy the lift of your wings. And you gotta have lift for your airplane to fly. So how do we avoid frost? Well, one way is to keep the aircraft inside at night. If you do leave it outside, clean off the frost, especially on the wings, or just wait for the sun to melt it off. I hope this video makes you a safer pilot, but it wouldn't hurt to watch one more video to learn something else you can bring with you into the sky. Try this one out and I'll see you over there. See ya!
Aircraft calling. Stay position.